all to the International Conference on Sustainable Energy and Advanced Materials ICSEAM 2025, jointly organized by the Department of Chemical Engineering, Department of Mechanical Engineering, and Department of Material Science and Mechanical Engineering, also Department of Vocational Studies. Now I would like to brief about conference, the theme of conference and objectives and structure of the academic gathering. Sustainable energy is essential for addressing the intertwined challenges of environmental protection, economic development and social equity. By transitioning a clean and renewable source such as solar, wind and hydropower, we can significantly reduce greenhouse gas emissions, combat climate change and enhance energy access for underserved communities. In parallel, advanced materials including nanomaterials and high-performance composites are revolutionizing key industries such as aerospace, automotive and electronics by offering enhanced strength, reduced weight and greater efficiency. These materials also drive innovations in critical areas like solar energy, conservation energy, energy storage, water purification and carbon capture, contributing meaningfully to sustainability and technological advancement. Over the course of this conference, we will delve into a wide array of topics from conversion technologies to energy storage to sustainable material development and environmental remediation studies. I extend my sincere appreciation to our keynote speakers, invited experts and all participants for their valued contribution. We sincerely hope that this conference serves as a platform for knowledge exchange and interdisciplinary networking to deal with some of the most pressing challenges of our time. Once again, I welcome you all to this conference and I wish you a productive and enhancing experience. Now, I now request the dignitaries to kindly come forward and take their seats on the dais. Pro Vice Chancellor, Professor Sudhir Kumar. Our esteemed chief guest, Professor Lalit Chandra, Department of Sustainable Energy Engineering, IIT. Dr. Sudarshan Narayan, Department of Sustainable Energy Engineering, IIT. stage to present a plan to invited guest Dr. Narayan.
Honorable Vice Chancellor Professor Partner. Unfortunately, sir, on account of his ill health, is not with us today, but he has joined us online. Pro Vice Chancellor, sir, Professor Sunil Kumar Avasthi. Our Chief Guest, Professor Lalku Chandra. Our Keynote Speaker and invited guest, Dr. Sudarshan Narayanan. Registrar, sir, Dr. Anil Kumar Yadav. Deans, Directors, our special guests from HPTU, AITH, and my dear colleagues, conference participants, and dear students. On behalf of the School of Engineering and Technology, Chhatrapati Shahu Maharaj University, I extend a very warm welcome to all the participants at the International Conference on Sustainable Energy and Advanced Materials. This two-day conference is being conducted in a hybrid mode and is jointly organized, as was mentioned, by the Departments of Chemical Engineering, Mechanical Engineering, Material Science and Metallurgical Engineering, and the Department of Vocational Studies. At the very outset, I would like to extend my heartfelt gratitude to our very dynamic and visionary Vice Chancellor, Professor Vinay Kumar Pathak, whose unwavering support and inspiring leadership has made this event possible. My sincere thanks to Professor Sudhir Avasthi, our Pro VC sir, Registrar sir, Finance Officer sir, who have always supported us in every step of the way. We are truly honored to have amongst us distinguished gathering of scholars, including our chief guests, Professor Chandra and Dr. Narayan, from the Department of Sustainable Energy. We are grateful to both of you for sparing us your time. Chhatrapati Shahu Maharaj University, established in 1966, stands as one of the largest and the most esteemed state universities of Uttar Pradesh, with a wide spectrum of academic disciplines, including science, engineering, law, management, pharmacy, health sciences, arts, humanities. The university plays a very vital role in shaping the intellectual and professional landscape of this region. In the recognition of its pursuit of excellence, CSJMU has been awarded the NAC A++ grade in 2023 and has earned the status of the UGC Category 1 university. It has also recently secured QS Asia ranking of 263 in the South Asia categories. We are also very proud to say that CSJM University has been featured in the QS Sustainability Rankings of 2025. The University Institute of Engineering and Technology, a constituent institute under the School of Engineering and Technology, CSJM University, was established in 1996 and proudly marks 29 years of academic excellence. UIT offers undergraduate and postgraduate programs in computer science and engineering, artificial intelligence, electronics and communication engineering, mechanical engineering, chemical engineering, material science, metallurgical engineering, nanotechnology, as well as specialized programs in computer applications and designs. Our graduates have made significant contributions across academia, research, and the global corporate sector. The theme of this conference, Sustainable Energy and Advanced Materials, is of immense relevance in the current world. As the global community faces the challenges of climate change, energy security, and resource efficiency, The role of sustainable technologies and next generation materials is more critical than ever. Over the next 2 days, we will engage in exchanging research initiatives and spark conversations that may shape the technologies of tomorrow. Considering the relevance of this theme, we have received a good response in terms of submissions. There have been 125 submissions and 73 of them have been selected for presentations in 8 sessions, including both offline and online. We have received contributions from prominent institutions like IIT Kanpur, IIT Kharagpur, IIT BHU, MNIT Jaipur, NIT Bhopal, NIT Patna, CIPET, HPTU, IIT Lucknow, and other colleges of APTU, to just name a few. A special word of appreciation goes to the organizing committee, the conveners, co-conveners, and our dedicated student volunteers whose tireless efforts have brought this event to life. As we embark on these 2 days of inspiring keynotes, insightful sessions, and valuable networking, I encourage all of you to collaborate and share ideas. Once again, I warmly welcome each one of you to this conference and hope you have an enriching and memorable experience. Thank you.
May I request all the dignitaries on the dais to please come forward for formal release of book of abstracts of the conference. Honorable Pro Vice Chancellor of ICSEAM Kanpur University. May I invite him to address the gathering.
The dignitaries on the dais, Chief Guest Professor Chandra, Professor Sudarshan Narayanan, Professor Vesti Mitra, Director UIT, all the researchers, policy makers, students. I'm really pleased to be here in this conference, international conference, which is devoted to the sustainable energy and alternative sources of energy in the form of new materials. As the global demand for energy surges and the impacts of climatic change become more apparent, the quest for sustainable energy source has become paramount. Central to this mission is not only the development of clean energy technologies, but also the advancement of materials and new materials rather. Together, sustainable energy and advanced materials are shaping a more resilient, efficient, and eco-friendly world. Sustainable energy refers to the energy derived from resources that are naturally replenished and have minimal environmental impact. This includes solar, wind, hydroelectric, geothermal, and particularly the biomass energy. Unlike fossil fuels, these sources do not emit the large amount of greenhouse gases, making them crucial in combating global warming and reducing dependence on non-renewable resources. This transition of sustainable energy is not only an environmental necessity, but also an economic and social opportunity. Investing in renewable energy creates jobs, improves public health by reducing pollution, and enhances energy security by diversifying supply sources. The development of sustainable energy technologies is heavily reliant on the development of advanced materials. These materials possess unique mechanical, electrical, thermal, chemical and other relevant properties that enhance the performance and efficiency. We have many examples of energy storage in the form of the new batteries, the wind turbines, fuel cells, hydrogen storage, and particularly since I belong to life sciences background, the biomass energy is also playing a role. While the potential of sustainable energy and advanced materials is immense, several challenges remain. High cost, scalability, durability, and integration with existing infrastructure are some of the hurdles that must be overcome. However, ongoing research and innovations are addressing these issues. Researchers are developing self-heating materials that extend the lifespan of energy devices. Artificial intelligence is being used to design new materials with desired properties faster and most cost effectively. Circular economy principles are being integrated into material design to ensure recyclability and reduce waste. The synergy between sustainable energy and the advanced material holds the key to a cleaner, more sustainable future. Governments, industries, and academic institutions must collaborate to invest in research, support green technologies, and promote policies that encourage sustainable practices. Education and public awareness are also playing a vital role in driving demand for cleaner energy and responsible consumption. By harnessing the power of science and innovation, we can transition to an energy system that not only meets our needs but also preserves the planet for future generations. As far as the environmental and economic drivers are concerned, traditional energy sources, primarily fossil fuel, coal, oil, etc., and natural gases, have contributed significantly to greenhouse gas emissions and air and water pollution and environmental degradation. These emissions are a major cause of global warming, rising sea levels, and increased frequency of extreme weather events. Moreover, the fossil fuels reserves are finite and geopolitically sensitive, making long-term energy security uncertain. This transition to sustainable energy systems is therefore not only an ecological necessity but also a strategic and economic imperative. We have various forms of sustainable energy like solar energy, like wind energy, hydropower, geothermal energy, and biomass and biofuels also. We have new set of batteries which are energy storage materials like lithium-ion batteries, solid-state batteries, sodium-ion and zinc-air batteries also. And recently, the graphene offers ultra-fast charging and high conductivity suitable for supercapacitors. As far as fuel cells and hydrogen economy is concerned, fuel cells convert hydrogen into electricity through electrochemical reactions, and we have many kinds of fuel cells also. Lastly, since I belong to an institute inside this university, which is Vidyal Shoikin, which is devoted particularly to study the Prachya Vidyas, the traditional knowledge of that is called the Indian knowledge system, ICSEAM. I must say that we do have 7 energy centers present in our body. Physiologically speaking, those who have studied neurosciences, they know that we have 7 chakras present: the Mooladhara chakra, the Swadhisthana, the Manipur, the Anahat chakra, Vishuddha chakra, Agyachar chakra, and Sahasrara chakra. These are the forms of the internal energy, which is called Antas Urja. If we ignite these chakras, which are the centers of energy, then we can achieve what we want. So I believe that these sources, which are the eternal sources of untouched energy, should also be activated. And lastly, since I belong to a discipline which is called life sciences, I must see solar energy as the best source of energy which is providing photons to our body. It is ironical to see that only plants are capable of capturing these photons, and these photons, the photon is energy, or the energy situated in the solar system, is being converted into the chemical energy, but we are not able to actually capture photons and convert them into the food material which plants are doing. So if it is possible that the chlorophyll which is found in the plants can also be obtained by the human beings. We know the structure of the hemoglobin, and chlorophyll is 90-95% similar. If we are able in coming few years, this utopian idea may also be, it will be converted into the reality, that if we become able to convert this hemoglobin into chlorophyll, the chlorophyll can also make us enabled to capture the photons and convert it into the chemical energy. So with this utopian idea, I would like to say that the sustainable sources of energy should be searched out. The discovery is must, but you must look into your body, which is also a source of eternal sustainable energy. Thank you very much.
Thank you, sir.
Now we are honored to have with us Professor Chandra from Department of Sustainable Energy Engineering, IIT Kanpur. May I invite him to enter the gathering and let us know about the importance of sustainability in the present day scenario. Sir.
Vice Chancellor Professor Maharaj, Honorable Vice Chancellor Professor Awasthi, my dear colleague, Darshan, Director of Engineering, Professor Mitra, and the Registrar Anil Kumar. I must say I'm humbled and really honored to be here, standing in front of you and talking to you. At the theme, International Conference on Sustainable Energy and Advanced Materials, I think this is a very timely topic. Timely in the sense it's relevant both technically, economically, and socially. When we develop technology, what's our objective? We always aim for efficiency in one or other. And as Professor Awasthi was stating, that the need of the hour is developing technology that is sustainable, technology itself, and aiming at high efficiency for societal applications. For example, can generate power from various sources like coal, oil, etc. Then why are we moving towards sustainable energy generation? When this is already existing, the lights are on, you are having, then why the need for sustainable energy? Because we realized in the due course, sustaining the entire value chain, maintaining the quality of life is extremely difficult, in fact counter thought process. Therefore, we are heading towards sustainable energy solutions. But when it's a solution, it entails several small to large sub-components. Material is one of all those components, which may and which will eventually enhance the sustainability and efficiency of this system. I have a presentation which is lined up. I will share with you some of the technologies we are working with. But the most important aspect is topics that are covered in this conference. I have gone through the abstract. There are really very many topics are covered, and I hope many of the new generation students, especially those who are in UG and PG, aiming for the research career, will benefit from these deliberations by very, very good speakers. Without taking much time, I would like to really thank all the organizers for putting in such a very many presentations, worthwhile to look at, contextualized, and oh, my voice is not audible at the backside? Okay. So I think I would like to really congratulate and thank the organizers who have put really a very hard work, so many presentations which are contextual and timely, share with you the latest findings in the area of science and technology, both fundamental and technology aspects of the systems. And I hope these few days will be memorable for those who are presenting and those who are listening to these deliberations. With this, I would like to thank you once again for inviting me, and I'm honored and humbled to be here once again. Thank you so much.
Thank you, Professor Lal.
Now, I would like to call Dr. Vishnumitra to present a token of appreciation to Pro Vice Chancellor Professor Sudhir Kumar Yadav sir. With Sudhir Kumar Avasti sir. Sorry, my bad. Now I request Dr. Abhishek Chandra to present a token of appreciation to our chief guest, Professor Laltu Chandra. I request Dr. Praveen Bhai Patel to present a memento to the invited guest, Dr. Sudarshan Narayan. I request Dr. Arun Kumar Gupta to present a memento to Registrar Sir Dr. Anil Kumar Yadav. Now I would like to request Architect Prashant Singh to present a memento to Professor Drishti Mitra, Director UIT. Now, to conclude the inaugural session of the International Conference on Sustainable Energy and Advanced Materials ICSEAM 2025, I now invite Dr. Anil Kumar Yadav sir, Registrar CSJM University, to deliver the vote of thanks. Sir.
Thank you, madam. Good morning to all of you. We are here to inaugurate the International Conference on Sustainability, Energy and Advanced Materials, jointly organized by 4 departments of the UIT, that is the Department of Chemical Engineering, Mechanical Engineering, Material Science and Metallurgical Application Studies. These are under the umbrella of School of Engineering and Technology, First of all, I would like to congratulate to all the head of the department, all the four the department and their faculties for organizing such a wonderful conference. On the dais, Honorable Pro Vice Chancellor, Professor Sudhir Kumar Vasili, Chief Guest and Speaker of the conference, Professor Chhatrapati, Department of Electrical Engineering, Department of Energy and Sustainable Energy, IIT Kanpur, Professor Sudarshan ji, Dr. Rishi Mitra, Dean and Director of the School of Engineering and Technology, and all the faculty members of UIT, Organizing Committee of the conference ICSEAM 2025. In this conference, we come together to discuss the recent advances in sustainable energy and advanced materials are driving significant transformations across the various sectors. So here we have the expert who will deliver, address the gathering about the sustainability. It is a recent topic which not only the energy engineering department but also in various fields. This is a very much attracting in the present scenario. Here are the three important things: environmental sustainability, protecting ecosystem and reducing carbon emissions. Social sustainability, equality, access to basic services, cultural diversity, economic sustainability, long-term business models, and don't harm the environmental society. So these are the few important things, just like as that cover the SDG goals and sustainability, net zero carbon goals, green hydrogen, circular economy, no poverty, zero hunger, quality education, clean and water sanitization, affordable clean energy, climate action, and more. So, expert will focus on these areas, and I have seen this booklet which is inaugurated today. A lot of paper mentioning the sustainability, energy, etc. Next generation wind turbines, solid state batteries, sodium ion batteries, gravity based energy storage, how EVs are affecting all these, smart grid and decentralized energy, how AI driven load balancing is there, blockchain in energy trading or vehicle to grid, how can be implemented in this? AI and grid, smart grid also there, how AI for load forecasting reduces space, balances variable and solar wind wings, smart meter and demand responses, real-time usage of monitoring and pricing, reducing the grid strain. Decentralized microgrid, all these things we are going to listen the expert in the days to come, the 2 days. Similarly, there is a fields of material sciences also there, how nanomaterials, nanoparticles, how can we impact on the other things. So for these things, I would like thanks to the expert who has come from the IIT Kanpur, and who will deliver his speech in the coming times. So I would like thanks to the first of all Professor Lalto Chandra ji, Department of Sustainable Energy and Engineering, IIT Kanpur, and Professor Sudarshan Narayan ji from IIT Kanpur, and a lot of speaker is also over there who will deliver the notes. And I will also thanks to the Pro Vice Chancellor sir, Vice Chancellor Professor Vinay Kumar Pathak. He is not over here, but I will also like thanks to him for providing the environmental and the atmosphere which are going in the campus to holding the international conferences in the past 3 or 4 months. I would also like thanks to the Director of UIT, Mr. Mitra ji. In his leadership, this conference is going to be held, and all the faculty members of this UIT and all the faculty members of the organizing committee, advisory committee, and reviewer committee who has reviewed the paper, and all the deans, various faculties, head of the department, delegate, participant, student volunteers, staff volunteers, and hospitality in charge, state officer, who is also part of the chemical engineering. So I would like thanks to all the student participant who is present over here, and all the media persons who is over here. And once again, I would also like to thank all of you. Thank you.
Thank you, sir, for your generous and motivational words. Thank you once again. May I now request everyone to please rise for the national anthem. With this, we formally conclude the inaugural session, thanking all the dignitaries for their gracious presence and thoughtful words. We now request all the dignitaries on the dais to kindly take their seats in front row so that we can start with the keynote address by Professor Chandra. Is lined up keynote address by our chief guest.
लग तो रहा है परमानेंट हो जाएगा। काम है क्या? बताओ बताओ, फोन कर लेना।
As we gather to discuss the needs and conflicts express my sincere appreciation to our keynote speaker, Professor Chhatrapati. I would like to present his brief bio sketch in front of you. Professor Raju Chandra is currently a professor in Department of Sustainable Energy Engineering at IIT Kanpur. Professor Chandra received his doctoral degree in 2005 from the University of KIT Germany. Subsequently, in the year 2005 to 22, he worked as a visiting scientist at the ICSEAM, India, and a postdoctoral fellow at INP, Grenoble, France, R&D consultant at the Energy Center, the Netherlands, and as a faculty member at the Indian Institute of Technology, Jodhpur, Varanasi, India. His research interests include computational and experimental fluid flow and heat transfer for designing the solar thermal subsystem, system for heat treatment of metals, and thermocatalytic hydrogen generation. Also, development of Russell number correlation of heat transfer with nanofluids. Bubble dynamics is thermally stratified fluid layers and investigating the transport, deposition, and mitigation of dust on solar thermal subsystems. The findings from his research has been reported in more than 95 peer-reviewed international journals, book chapters, and conference proceedings. He is a member of National Level Committee for the implementation of hydrogen-related applications in India and one of the author of the Hydrogen and R&D Roadmap of India. May I invite Professor Raju Chandra to deliver the keynote address. Sir, please welcome him. Big round of
Once again, good morning. Second time. I'm the opening batsman of the next 2 days. The difficulties and the challenges, the benefits are that I can play all the match, all the 50 overs in the 1 day, or I can get out very quickly. I will try to play my part here as the opening batsman, but in the challenges that I have to open the conference to make you aware of certain terms before you get into more detailed discussions. So just from my understanding, how many of you are at undergraduate level? You may raise your hand. That would be wonderful. Excellent. Now that gives me a motivation to introduce you to the topic even more. So please stop me any time and ask questions. Anytime you feel comfortable. Do I have any changes? No problem. Otherwise I'll use idea. You see the opening back? Thank you so much. Let's get back to the presentation. Yeah, thank you so much. So if you look at this picture, purposefully I've taken this picture, and this is a bit without any color. Does it look good to you? How many of you like this picture? This is IIT Kanpur picture. The topic is energy, sustainability and innovations. So I'm trying to introduce you to all these topics and some ideas that we are working on at the end. So this picture, how many of you like it? Students, would you like to see your houses painted gray all the way? Fine? No, I don't think so. Let's look at the right picture. Okay. Now this is the right picture. Which one of, I mean, now do you like it? It looks more colorful. So what was the difference between the previous picture and the current picture? The color was missing, right? Everything else was there, the color was missing. That is all about sustainability. When you mix all the colors, your life becomes great, you leave that early picture. I hope you don't want to leave it. Right? But you cannot live without energy. Can you live without energy? In thermodynamics, we heard about open and closed system. All of you are open systems. Why? Because you breathe in and out. Naturally open systems, right? You cannot live without energy, but at the same time, you don't want to be gray color. There has to be a way in between. That's the whole idea. What is this? A bulb, which glows every day. Green, the backdrop. The bulb has to be there, but green has to be there as well. Otherwise, you will have that colorless picture. Right? So, all of you are very aware, but still, to put the awareness more, what is energy? How do you produce energy? All of you know thermodynamics, atomic level. So energy, you need to do any work. It's a need, it's not an option. You cannot live without energy, right? So be it fire, you burn it, generate heat, right? It's hot. This is a metallurgical process where you work on the metals or materials. You need energy. Electricity, you need energy. You cannot live without energy. Do we agree to that point? We cannot live without energy. At the same time, we don't want to be green. We have to be green and have a lot of energy for our daily needs. That's what we at least acknowledge now. So let's move ahead. So why do we need energy? For any work that you can think of, be it cooking, bathing, agriculture, transport, even wars. Why do you need more energy for war? You think? Nowadays, the Russia-Ukraine war is ongoing. Have you heard about it? Who is winning the war? You don't know. The one who has more energy will win. Do you agree with that definition? So energy is also needed. This was early French Revolution, but now this is not the case. To fight with missiles, you need energy to fire the missile, right? Bigger missiles you fire, more devastation you make. So energy has a flip side. A lot of energy can cause devastation as well. You have to use energy judicially, not to cause devastation, but to create. Like agriculture is creation. You need transportation, but you don't want to do devastation. But you need still energy for all activities. You do daily, morning till evening, you cannot leave. The food is the source of pure energy, right? How? Because food has a calorific value. That's what you utilize, consume and utilize, right? Somewhere. So now it is modern energy. We produce using big power plants. Anybody knows what these structures are? These are cooling towers. And what are they generating here? What is this? Huh? Any idea what are these? The smoke's coming out, right? Why? Because you're cooling the water internally so that the power plant runs without any problem. So this is actually waste of energy. You know, waste of energy? So it's actually waste. But thermodynamics says you cannot run a system without having a sink and source. So this is sink. Your sink, so your sink is your atmosphere, infinite sink. Now what is happening? You are generating power and you are losing energy to the atmosphere. Good or bad? Why bad? You need energy, electricity. Can you run this room without electricity? Why it is bad? Anybody knows what fraction of energy gets lost in the process of power generation? What fraction? Let's say you put in 100 kilowatt each. What is the efficiency of these power plants? Typically 35-40%. Where the 60% goes? Loss. That's called waste heat. Now think about it. In reality, you are wasting 60% of the heat or energy that you produce by burning certain fossil fuels. Or even nuclear reactor, they use reactions, right? So 60%, if you don't utilize it or reuse it or recover it, what are you doing? You are not doing justice to the environment. So be very careful when you use energy, you must realize that you are wasting as well. reduce the waste, efficiency will increase. Therefore, I talked about in the opening discussion, efficiency. So if you reduce this wastage, the overall efficiency of the system will increase. But reducing the wastage, you need to work on it. It's not a gap enough. You have to work on the individual component of such system. There are many individual small elements. Please understand, developing a system is not one component, it's an entire system. Make it work together. You are a system. If any of the part doesn't work, you don't become well. You have to develop system which is efficient, energy efficient, don't waste a lot of energy. It's a challenge, real challenge. So their innovation have to be there. You agree? Innovation has to be there. Now why do we need energy? The next question is why? Because the population has grown, the demand has grown. You cannot live in cave anymore. Right? You cannot eat the meat without cook or food without cooked. Right? You cannot eat them. You need energy for all any of this. So it's a growth. So growth is good, but at the same time it needs energy. You can see we started 1 billion, then 1.6 billion at 1900, then went up to 2.5 billion in 1950. What's happening? 6 billion in 2000, and now we are about 8 billion. Started from 1 to 8-fold increase. The energy demand will also increase, right? That's the whole idea. So you have different sources of energy. Traditional biomass, coal, oil, gas, still renewables are very in a small amount. So there's a huge potential that you reduce the coal consumption and increase the renewable energy utilization efficiently. Don't lose energy. So energy is a precious commodity. Don't lose it. Use it. So now we agree that this is the trend, and this trend will continue. Why? Because industrialization is happening. More and more we need energy for running the daily business. So as an example, I deal with heat. I'm just putting one slide for you to think. So this is the entire energy scenario. The data is taken from very old information, but new informations are available, but it's enough for illustration. So if you have a lot of energy requirements, about 360 exajoules, out of which 32% typically goes to industrial processes. Nowadays it may be more because industrialization is rapid. This number might have changed. And 74% of this industrial heat goes to, or industrial energy goes for heating, and some portion goes to electricity. So this may have changed in the recent days. But not to forget, it's the need. You cannot live without it. So you have different temperatures. So when you say, why do you need heat for different applications? Like you do milk processing, and you do a lot of other industrial applications. And the temperature requirements are different for all these different applications. So you need energy at different levels. So each of these levels, let's say 150 degrees, less than 150, 150 to 400, 400, they need different technologies. So you cannot use one technology for all these applications. The technology is selected or will be selected looking at the application. Otherwise, you will use a very complex technology which may not be needed for that application. So your selection has to be very carefully done and not random. Jo bhi mila, utha lo. Aisa nahi hoga. You have to be very careful, very logical. Right? Please stop and ask questions anytime. Now, for our understanding, I got this slide from my colleagues, so I thank all of them first. I really enjoyed looking at this. What I was looking at, you eat apple, banana, now a diaper change, washing, and a McDonald's meal. Each you have associated CO2 emission. CO2 is carbon dioxide. It is not good for atmosphere. You also emit. It's not good for atmosphere. Each of these emitting, so 10 gram or 10 to 150 gram per apple is a lot. सोचा है कभी? नहीं सोचा. आज सोच रहे हैं. देखिए. अब ये देखिए. You wear pants and how often you clean? No, you are emitting energy. Oh, so CO2. Food, you are emitting CO2. This is, what is this? मोबाइल फोन सबके हाथ में है ना, सब थर्मोमीटर है, कुछ हो जाइए। कार, बिगर द कार मोर द एमिशन, और क्या क्या है हमारी लिस्ट में? ये बस 250 किलोग्राम फॉर 500 किलोमीटर बस ट्रिप, 1150 किलोग्राम फ्रॉम मुंबई टू दिल्ली। आगे से फ्लाई करने से पहले हमें सोचना पड़ेगा what are you contributing? No, but these are facts. What is this doing? All these emissions. Deforestation, look at this. If you remove 2.5 acres of land, you will contribute yourself 500 tons. I was very happy when I entered JMU University. I was telling Mr. Lee. I was really surprised. Very nice campus. I wonderfully enjoyed it. Wonderful. Keep it clean. Make it clean. So this is again a very, very difficult task. Please see these facts before you act. And what we know, pollution. Eventually we call pollution. Everything leads to a pollution. So what we do, human needs energy, everything leads to some kind of CO2 emission and pollution. जो हम ग्रे कलर देख रहे हैं, ग्रे शेड, वही है। But we cannot live without it. So where we stand right now? इतना सब तो देख लिया, where do we stand right now in terms of the story? This is where we stand. Or maybe we will be standing in a few years. Here is industrialization and here is no water. So will any thermal power plant run without water? अब सोचो कैसे रन करेंगे ये पावर प्लांट फ्यूचर में? There is no water available in the vicinity, or the water quality goes down. कैसे रन करेंगे? तो आप ये सोचना। और ये तो जानते हैं, दिस पिक्चर इज वेरी वेल नोन। क्या है ये? दिख रहा है ये? नहीं दिख रहा है ठीक से? क्यों नहीं दिख रहा है? कहाँ से आया ये? आया कहाँ से? कहीं ना कहीं हम कंट्रीब्यूट कर रहे हैं ना। नेचर ने तो क्लीन दिया था, हमने कंट्रीब्यूट किया। तो ग्रे कलर पहला शीट, दिस ग्रे कलर इज आवर लाइफ नाउ। Either you live with it or deal with it. Would you like to live with it? The new generation, obviously you have to deal with it, right? You have to solve this problem. You cannot live with this problem, but you have solutions. There, my colleagues and many will discuss through these 2 days, and I'm sure some of these solutions you can pick up in future to work on. Therefore, these slides will guide you and motivate you for doing this. And I really now another picture. Daily picture, right? In Mumbai, आप में से कोई मुंबई गए हैं during many seasons? यही पिक्चर दिखेगा आपको। तो पानी कहाँ से आया? जब हमारे पास पानी नहीं है ना, we don't have water. Where is all this water coming from? कहीं बाढ़, कहीं सूखा, समझ ना रहा है? Somewhere there's no water, somewhere this situation. Why? Because there's imbalance in the system. Anybody know why this imbalance happens? जो हम देखते भी नहीं, सोचते भी नहीं, अब थोड़ा वहाँ तक चलते हैं। यहाँ तक है प्रॉब्लम। ये सी लेवल चेंज ओवर द लास्ट years. -20 means going down and +20 means going up. 1993 to 2018 आप में से बहुत लोग इस एरा में हैं। हम लोग इससे थोड़ा पहले आपको इसके बीच में। But this has happened. So what is happening? The sea level is rising at many areas, many parts of the world. I'm not warning you, but it's fact. न्यूज़ फॉलोगे पता चलेगा। तो कॉन्सिक्वेंस क्या होगा? कुछ सिटीज विल बी आउट फ्रॉम द मैप। कहाँ जाएगा? पानी के नीचे। वहाँ क्या करेगा? जो वहाँ रहते हैं वो मूव करेंगे दूसरे सिटीज पे। तो द माइग्रेशन विल स्टार्ट, कंजम्पशन विल चेंज, पैटर्न विल चेंज, ह्यूमैनिटी विल सफर। And why these are all happening? Because we have not taken care of many things during the process of development. हमने सब कुछ तो कर दिया, but we have never looked into this situation. Now this situation is there. देखिए पिक्चर, ये है आइस कवर ऑफ एंटार्क्टिका। अब जानते हैं क्यों जरूरी है? Because of the natural balance of temperature of our globe planet. ये necessity है, ये option नहीं है, necessity है। अब देखिए हुआ क्या है? 1921 you had done its glacier. 2007 अब जब पिक्चर लेंगे तो शायद ये भी नहीं दिखेगा आपको, जो थोड़ा सा बचा हुआ है। तो ये है ग्लोबल वार्मिंग, जो हम सुनते हैं ये है ग्लोबल वार्मिंग। इसको कैसे एड्रेस करेंगे? प्रॉब्लम तो बहुत बड़ा है, वी नो दैट इज द प्रॉब्लम। So then people thought, when they looked at all these problems, क्या करें? Sustainability word emerged, right? Sustainability हम सब जानते हैं. So what is sustainability, especially UG guys? What is sustainability? What do you think? Why sustainability? अब ये सब तो story हमने कर लिया last 10 minutes से, but why sustainability? What is sustainability? है क्या भाई? अभी तो हम बातें सुन रहे हैं. What is sustainability? हाँ? जोर से बोलो, सुनाई दे रहा है. यहाँ तक नहीं आ रही आवाज. Balancing what? Now energy आपको चाहिए. डेली लाइफ में आप कैसे सस्टेनेबिलिटी करेंगे? आपके लाइफ में क्या करेंगे? अब बताइए. Yes, but आप क्या करेंगे उसमें? आप डेली लाइफ में क्या चेंज करेंगे? क्या काम करेंगे? इस एसी को बंद कर देंगे अभी? लाइट ऑफ कर देंगे? नहीं ना, ये नहीं कर सकते. क्या करेंगे? हमें इनोवेशंस करने पड़ेंगे. We have to think out of the box, right? You cannot think inside the box and change the box. That's the problem. You have to go outside the box to expand the box. हम box को expand कर रहे हैं. So you have to go outside the box. You have to go outside the normal thinking. ये भाई हो जाएगा. नहीं, you have to go outside and think. How can I make a contribution? So each of your contribution will expand this box and help addressing this problem. Individual का नहीं है काम. सेनापति का काम नहीं है. पूरा सेना का काम है. Individual person cannot make change. So what is sustainability now? I was thinking yesterday, and my friend came in. I was telling him, see, I found what is sustainability, and I'm sharing it. I discovered it yesterday. Sorry to tell you. I put it this. You see the color? Sustainability. I said this is not one term. Actually, it's made of two very logical terms. They're called ability to sustain. Does it make sense to you? It's an ability to sustain. Now I found another term which was unproclaimed commission. So these terms are actually coined to make you aware. It is not myth anymore. ये reality है. आ गया हमारे सामने, खड़ा है. जो आपको pictures दिखा है वो हमारे सामने खड़ा है बिल्कुल. चाहे आप आँख बंद कर लीजिए. लेकिन this is the fact. You cannot live without it or live with it. That's all. So then there's a sustainable development is the development that meets the need of the present without compromising the ability of the future generation to meet their own needs. In एक लाइन छोटा सा, अगर हम कल जाएं तो आपके लिए वो दुनिया छोड़ जाएं, that you feel happier, और आपके लिए तो वही काम करना है. So that is why you need sustainability. ये ऑप्शन नहीं है, ये नीड है, नेसेसिटी है आज की डेट पे. ये बड़ा अच्छा पिक्चर मिला मुझे. हम रोज बेथिंग करते हैं, so some water goes out of the box. Now if you want to keep this box or keep this bathtub filled with water, you have to supply the same amount of water. You cannot supply less. If you supply more, this will be filled even more, right? You will have more water. Similarly, you cut trees, you have to plant trees as well. तो करना क्या, लॉजिकल क्या है? How to sustain? The simple logic. Drain the bathtub output or consumption. This is the draining. Should be less than equal to filling the bathtub. The replenishment rate should be positive. You should positively replenish. Yeah, logical sense है. यही करना है हमें. हम जो यूज करते हैं उससे ज़्यादा क्रिएट कर लें. जितना कार्बन डाइऑक्साइड हमने कंज्यूम किया उससे ज़्यादा कहीं पे एब्जॉर्ब कर लें. अगर आपने ये काम किया तो आपने कंट्रीब्यूट कर दिया. That's all. इसका मतलब ये नहीं कि कल से सारे क्लासेस बंद. ये नहीं है. इसका मतलब है आपको काम करते रहना है. साथ में with the work you do, you add a few elements from your side. ये करेंगे. बट आपको ये करना पड़ेगा. हमें भी करना पड़ेगा. हम बोल तो रहे हैं कि हमें करना पड़ेगा. हम कर क्या सकते हैं? Add some innovation elements, something. So I said these are very big questions. We cannot address with one person. We cannot do that. But each individual together, you make a team and you can address, right? So then the last part is like how to address such irreversible challenges. You cannot make them back again the same way. But आप कुछ कम कर सकते हैं. ऐसे करिए. So answer is innovative, efficient energy system that I started my discussion. Right? Then is renewable energy-based energy generation, storage and utilization. We are talking about it, and I will use some examples from the research I do now. अभी तक मैंने आपको थोड़ा story telling किया. अब थोड़ा सा टेक्निकल बातें बताऊंगा. So here in the department we are working on many facets: energy generation, storage, and so. So generation from all different renewable sources or sustainable sources, solar, wind, hydrogen. And waste to energy is very important. You don't want to waste a lot. Otherwise, everywhere you will find dump yard. उसको भी energy में convert कर सकते हो, right? But storage is very important. If you generate energy and if you waste it, you will not have much energy left, right? You have to store energy. So storage is also very many applications. So those who are interested, please visit our website to see more information. Distribution. When you generate energy, efficient distribution is very important. Because if you lose energy during distribution, this is not good either for the energy itself. Because you lose everything to atmosphere. Please remember, you don't lose it anywhere else. You lose everything to atmosphere. Then policies. All this can happen if policies are in place. That means some thoughts are in place. Some people agree that okay, hey, karna hai, then things will happen. Somebody can talk. So then the policy has to be environmental impact, financial impact, and social impact. Like I told you, if you have to buy medicine every day, then it's a financial impact, your health will be affected and so on. So there is an impact. You have to work on it. So at the innovation side, I'm showing you some examples because these are the things I do, so I put it at the end. So at least you have taste what we do, some technical taste. So solar thermal based power, heat and hydrogen generation, this is what I actually do. So this is a system, you may not be aware, but I will tell you, if you are aware, it's very good. What you are looking at, the sun is shining brightly. And the radiation is falling on these mirrors. These are mirrors, but what mirror does is reflect. So this mirror has a particular shape, like parabola. This is a parabolic shaped mirror, so parabolic front. So these mirrors reflect the radiation through these lines. Like those who are in mechanical, chemical, or any system, they will imagine if I reflect this energy on the lines, or there's a tube, what will happen? The tube will heat up. Okay, na? Obvious logic. Hai? What you can do, you can flow cold fluid, and the cold fluid goes through the tube, becomes hot fluid, comes out, and it goes to a heat exchanger where the fluid comes indirectly in contact with this water. So here, this cycle is water and this cycle. So hot fluid and water. So water enters the heat exchanger and it becomes steam. And here the hot fluid enters, it cools down and the cycle continues. So what here? Radiation is focused, so this is called focused. So radiation is focused. Sorry. I put 25 minutes. It's over, but I think I'll take more. Okay? It's not my phone. Okay, so this is the situation. So here steam is produced and the steam is running a turbine producing electricity. So what have we done here? Can you identify what problems we are addressing? Anybody? We are not using any fossil fuel anymore. The CO2 emission has been reduced. See that? This is possible. आपको सोचना है and technology हो सकता है. Efficiency wise, you have to work on. So what is it now challenge? What are the challenges now from the slides that we have seen? Efficiency, how to reduce the losses, right? Those are the challenges. अब इसको deal करो. Those are technical challenges. आपके bright minds से solve हो सकते हैं. But this is one way. Another way that you have lot of mirrors again reflecting radiation on this particular shape is called receiver, which heats air, and you can use hot air to run a Brayton cycle. वो भी कर सकते हैं. तो हुआ क्या? आपने you created power out of solar radiation, electrical input, electrical output from radiation. Another technology is photovoltaics. My colleague will talk about that. So this is thermal. Then another is photovoltaic. So there are different ways of generating power from solar radiation. So therefore you reduce the carbon dioxide emission, and that is the huge contribution. You don't burn coal anymore, right? Another technology we use, just like quickly. So we do heat treatment of metals. I mean ductility, flexibility of the metals. How do you make it flexible? You heat treat it. So heat treatment is a very energy intensive process. There you need typically gas or coal-fired electrical energy. So you use electrical energy for heat treatment of metals. And the problem here, electrical energy thermodynamically is the highest grade energy and heat is the lowest grade energy. अब कर क्या रहे हैं? heat से electricity produce कर रहे हैं. Of electricity you are using for heating. Makes sense to you? How many of you agree to this? पहले you generate heat, then you generate electricity, and then you use electricity for heating again. Does it make sense to you? Thermodynamically disaster. But we are doing it day in and out. Why not thinking of it? So you generate heat and utilize it. Make simple solutions. So without going much details, so we have created such a technology where radiation gets focused on this receiver. Receiver means you receive the radiation, and then receiver provides you hot air, and the hot air can be used for metal processing. Very simple. लगता है ना बहुत simple है, but ये actually हो चुका है. तो आप लोग थोड़ा सा अगर सोचेंगे तो innovations will be there. You have to just use your basic knowledge. Innovations कुछ अलग सा कुछ नहीं है, बेसिक चीज है. इसमें मैं ज़्यादा चीज़ें नहीं. Actually एक system है जिसका schematic यहाँ दिखाया है. System, the system which was developed, implemented, tested, it's all done and it is there. So you can think, you can do more innovations. Now the question will be immediately industry may not take it. That's fine. But as a researcher, our job is to bring technologies which may come 10 years down the line. ऐसा नहीं है कि आज ही किया कल आ गया. ऐसा नहीं होता है. There may be a time lag and we have to accept that. So you have to keep developing ideas, technology, so that future somebody looks at it. Hey, okay, there is such a thing. Let's take it over. That's one example. Another is hydrogen. We heard about hydrogen. How much? How many of you know about hydrogen? I think all of you know. So why hydrogen? Because it's clean and environment friendly. But do we have hydrogen available? Can we capture it? No. We have to produce it, right? So hydrogen, as you know, it has very high LHD and HHD compared to any other diesel, petrol, and natural gas. But hydrogen is not available for you to use. You have to produce it, right? So applications you can use in power, transportation, power, storage, and industrial processes. So all sectors in future will make use of hydrogen. But hydrogen आएगा कहाँ से? Generate करना पड़ेगा. तो fuel cells, etc. These are different ways, and I am showing you another way. Again, an innovation I am showing you. So here at IDECA, we are developing a system which can produce hydrogen. So you know ammonia. Ammonia is a very standard chemical which is used widely, worldwide, and in India. And ammonia has nitrogen and hydrogen. You know the problem with hydrogen is even if you produce it, you cannot transport it. To transport hydrogen, you need 1,100 bar. 1,100 bars. आपके सर पे कितना बड़ा है? How much pressure you have on your head? 100. उसको 1,100 times increase कर दीजिए. That much you need. The challenge is the transportation. So therefore, we are looking at alternate ways of transporting. Ammonia is a natural, it is a liquid, or it's a chemical that can be maintained at liquid state at even 10 bars, and you can transport it. So therefore, you see, it's a very simple logic. Makes sense? You use ammonia and don't. Ammonia, if you challenge here is how to make ammonia sustainable. So people are working on that. So there are two problems. One is trading and second is transporting and breaking. So we are working on the transportation and breakage part. You transport ammonia, it's very standard techniques are available. How to break it? We have developed a system. So here radiations getting focused here. This is the receiver, again the same logic. Ammonia you supply and the heat is utilized to break it into nitrogen and hydrogen. Make sense to you? Challenge क्या है इसमें? Challenge क्या है? Because ammonia is not a human-friendly chemical. So you have to deal with it very carefully. Second challenge क्या है? The system must be efficient. Third challenge क्या है? It should not produce lot of wastage. है ना? तो ये जो process है, it happens around 600 degrees Celsius. You can easily produce lot of wastage. So what we are working on, and just for your information, थोड़ा सा. Last slide. Okay, I think it's fine. No problem. So when we looked at the efficiency, it's called solar to hydrogen generation efficiency. Our calculations show that we can easily achieve more than 40% and we can even reach beyond 50%. 50% means you can use 50% of the heat energy to convert into hydrogen. And so net means whatever you supply, this is the supplied energy and this is the generated hydrogen, this is the number of moles of hydrogen. So you can do the simple exercise, but the innovation here is also involves certain waste heat recovery. Like I told you in the previous slides, so we have thought about it and included all possible best practices. You can still come up with ideas, sir, this is missing. So we are very open to discussion. If you have ideas, please come. We discuss openly. So innovations are not one day, but it's a thought process. Keep thinking and you will hit jackpot. Who knows? So keep thinking, my friends. Okay? That's my whole idea behind this presentation. The conclusions. The growing energy demand leads to greenhouse effect, जो हम देख रहे हैं daily. Sustainability driven developments are necessary to address the global challenges. ये भी हम सोच रहे हैं. हम कैसे करना है? Use of renewable energy technologies and innovations are the need of the hour. These are some conclusions that I have drawn from the presentation. Thank you for listening to the presentation patiently. Please feel free to ask any question. Thank you.
Thank you, sir, for your insightful and awakening talk. Thank you. Now I would like to ask audience, if you have any question, please ask. Anyone?
Madam is asking whether it is economically feasible or not. So there, this is called techno-economic assessment is the process that if you ask, it's a general question or it's a specific question? Okay, so techno-economic assessment partly have been done, and I'm just giving you a number. Literature, so therefore literature review part is very important for those who are aspiring for PhD. So literature shows that transportation of ammonia at 10 bar would cost 31% less than that of transporting hydrogen. Leave aside safety. And our first concern was safety. System should be safe. Transportation should be safe. You don't want to transport a time bomb through densely populated country like India. Like 1100 bar or 1200 bar is a ticking bomb. Small element, but yes, not that, but now technologies are getting developed for transportation here. Have you heard about 100 bar transportation? There was a news rapidly spread. आपने इसमें सुना है that the vessel has been developed to transport hydrogen 100 bar. So people are working on it. ऐसा नहीं कि नहीं हो रहा है. But at the same time, you have to think alternate ways. There will be many ways. Which of the way will hit the bottom line? That will be the time constant. But आपको काम बंद नहीं करना. You have to work on different ways to hit or solve one particular problem. So cost assessment is on well, but this is the first thing that we have looked at. Yeah. Any more questions? So those who are so there are two aspects. One is gravimetric density, that means energy per unit mass, and there is energy per unit volume, energy density. So if you look at the volumetric energy density of hydrogen is extremely low. It's about 0.02 megajoule per liter. That means you have to transport a huge volume of energy. To compress hydrogen to liquid state, it needs about 1000 bar or more. Therefore, if you want to transport a significant amount of energy within a small volume, the pressure has to be extremely high. The gravimetric or the kilogram wise is like 120 megajoule per kilogram. So 0.02 megajoule per liter and 120 megajoule per kilogram. Therefore, you have to compress it at a very high pressure to transport. And compression at high pressure also needs energy, compression. That also a very expensive process. you want to bring it to very high pressure, then only the effect will take place. But to bring it to that pressure, to bring hydrogen gas at about 1000 bar, the compression energy you need is significant. Or maybe even 20-25% of the generation energy, which is a very, very large number. Therefore, you have to think alternate ways. That's why people are thinking alternate ways of transporting and storing hydrogen.
We can entertain few more questions from the audience. Anyone? Student? Delegate?
I think I was very good. No more questions. No, that's all. I'm sure those who are in CHMU or anywhere else, if you have ideas, as I said, innovative ideas, you thought, feel free to contact us. We'll open to discussion. Don't think any idea is stupid. No idea is stupid. Only the one who listens and discards is stupid. Your ideas are always brilliant. Don't stop yourself. Okay? Keep contacting. We are there. Always keep in touch. Please.
For the alternative way, you showed, like, for example, the mirror one where we are concentrating the heat. Okay, so for that also.
Direction one, concentrating radiation.
Okay, concentrating the radiation. Okay. So to install all that mirrors also, you are also using that so much land, na? So.
Absolutely, you're right. Now, I call a very nice word, God plays dice. Now, why do I call it? You know, just if you can search Google right now, which part of India has the highest level of radiation? Can anybody Google for me?
Rajasthan?
No, wrong. It's Ladakh.
Okay.
But Rajasthan has also very high level of radiation, but the highest is at the Ladakh. Now think about Rajasthan. Who lives there? In the desert. Is it used? That's why God plays dice. God gives you both options. You have to choose it carefully. Ladakh, there are locations where nobody lives. And people can use those locations. Challenge. चैलेंज क्या है? राजस्थान में चैलेंज क्या है? लद्दाख में चैलेंज क्या है? कुछ सोच सकते हैं? लद्दाख में चैलेंज इज लो टेम्परेचर, हाई विंड स्पीड. राजस्थान में dust, wind speed, challenges comes with the. So you have new ideas, and there will be challenges. Now, अगर आप researcher, what do? You use the technology, you work on challenges. You have to work on the challenges. That is the job of you guys. Work and resolve those challenges. So yes, there are a lot of locations which are inhabited, not habited. You can make this system there, but there are challenges you have to deal with, and it is already getting there. Middle East, you will see, Middle East there. They have most of these installations, and in the US, the desert, Mojave Desert. These are the areas people are using for. Very good question. Thank you. Wonderful. Yeah. Coming to that question, good question. So this process is highly pressure temperature dependent. If you want on this pressure level of 1 bar, you can operate up to 600 Celsius. So why the efficiencies are low? The question is why efficiencies are low? Because we lose a lot of heat. If you reduce the heat loss, how do you do that? By using waste heat recovery. You don't lose it, so what you generate is nitrogen and hydrogen at high pressure. Sorry, at 1 bar and 600 Celsius. Both will get 450 or 400. So you don't leave it to atmosphere. You, first of all, you store or you utilize it right now, extract the heat and use it for the process itself. Bring it down to therefore waste heat recovery is an concept, and which will be there in almost any thermal system. Not only thermal but any practical system. Otherwise, you lose heat to atmosphere eventually. But this is not allowed.
If there is no question, then we conclude the session. Thank you all, and I would request all the dignitaries and faculty members to join us on high key downstairs.
Students may also proceed for tea at the designated counters, and will commence the second session of keynote speakers at 12:20. Please come back for the second session. Thank you.
focusing on enabling next generation solid state batteries. His current area of interest includes developing solid state lithium-ion batteries for mobility and stationary storage and exploring new materials for building integrated photovoltaic applications. He has 20 plus publications in international journals in the area of energy storage, advanced acceleration, photovoltaic and metal polymer composites. He also holds 8 US patents, 4 granted and 4 filed in the domain of multi-layer, spectral, selective coating and transparent conductors.
Thank you for the very kind introduction. I hope I'm audible in the back. Okay. Again, thank you, Professor Brishti, for this very kind invitation to be part of this session. And it's a real honor and a pleasure to be here from right across GT Road. And I've never been to a CHMU campus, but it's really, as my colleague Professor Laltu mentioned, it's a really beautiful campus, and I hope to visit here more often in the future. And so yeah, like we see in basically in IPL or any of our Indian cricket matches, when Rohit Sharma gets going, right? So it sets a very good setting for the Indian batting lineup. So I'm the opening batsman as well, but I'm not on the striker's end. I was on the opposite end. So finally, Rohit Sharma gave me some space to continue batting, but he's really set the stage for a very nice inning for this session. So today, what I'll do is I'll be talking a little bit about some of the stuff that we do, but talk a little about something that is closer to what we do here at IIT Kanpur in the Department of Sustainable Energy Engineering, particularly in my group, which is working on energy materials and devices for building sustainable solutions. And more particularly, or more specifically, something that I'm going to be talking about is tackling this twin challenge of energy generation as well as storage. So my colleague Professor Laltu did talk a lot about energy sustainability and why it's necessary, how it's necessary, how do we go about building sustainable solutions. But for that, we need to be able to generate energy, and generation of energy alone is not sufficient. We need to be able to store it as well. And it so happens that it's a twin challenge. It's not a dichotomy. So, and without really going too much into detail, since this has already been covered, we are really very hungry. We are hungry for energy. We need all our creature comforts. We need air conditioners. We need our gasoline vehicles and so on and so forth. So, if you look at the overall energy usage in the world, currently we are, and this is a plot that I think we've already seen before. Most of the energy consumption comes a lot from coal-based and oil-based sources, and our energy consumption is increasing manifold, almost exponential. So you can see that, and currently the primary energy consumers are the countries in Asia, although US and Europe do contribute significantly to this plot as well. Okay. So, and it turns out that only 1% of the overall energy generation, so if we look at renewable energy sources, primarily most of the energy that is being produced so far is from coal-based or oil-based sources. We saw a nice picture of a very nice thermal power plant, right? So all it is using is coal or any other oil-based sources to provide or produce all of this energy. And there is a lot of talk about, oh, we are going to install solar, we are going to install renewables, there's wind, there's hydroelectric, so on and so forth. But if we actually take a look at the numbers, only 1% of all of the energy that is currently being generated globally is from solar, and this is from the US Department of Energy estimates. So if you look at it going forward, and we are looking at projections across the next couple of decades, going on to about 2050, the projected consumption is going to be somewhere close to, and this, if we look at these numbers, this energy consumption is provided as in the units of 100 BTUs, and BTU stands for, it's called British thermal units, and sorry, this is in quads, okay, and one quad is represented as 10 to the power of 15 British thermal units or BTUs, which again is going to be converted into exajoules. Okay, it's not joules, it's not kilojoules, not megajoules, but exajoules, which means that's about 10 to the power of 18 joules. So that's a lot of energy. And if you want to really convert it to any sort of number that we can even comprehend, right? So we'll convert that into watt hours. Again, it's not a simple watt hour calculation. It's not watt hour, it's not megawatt hour, not kilowatt hour, gigawatt hour, but terawatt hours. So we are looking at exponential consumption of energy, right? Which means now the current consumption, especially in the US alone, is about 3 terawatt, and the global consumption comes to about 15 terawatt. And it is projected that over the course of the next couple of decades, we are going to reach an estimate of about 30 terawatt requirement as our total power consumption, of which US is going to basically consume 1/5 of that energy alone. And India, China being some of the really foremost developing nations in the world, we are going to be not too far behind. So it's really important for us to look at some of these aspects as we go forward. So I'll try to quickly go through some of these because I'm sure many of you are really familiar with many of these topics. So we call it the 30 terawatt question because for most of our lives, at least for most of us, people like me, my most productive time is going to be over the next couple of decades, right? So by 2050, I want to look back and see what have I achieved. I basically consumed terawatts of energy in my life, right? And so going forward, when we think about sustainability, we were always having this question after us, how are we leaving the world as, right? So that's an important question for us. So that's how we come up with this 30 terawatt question. How do we come up with this 30 terawatt? Right? It's not, obviously we don't want to use coal and gas because it's going to definitely, over the course of time it is really going to be detrimental for the planet. But what are our options? What other options can we look at? So of course there is nuclear. People have successfully harnessed nuclear power for energy, so you can get a lot of energy. But then these are, again, we've also heard stories of how mishaps can occur, and these can cause really catastrophes at a large scale. How about wind? There are wind turbines, there are wind units all around. But again, these are also not easily scalable, and there are only pockets where you can get good wind flowing so that you can actually generate power from that. Biomass, again, this would require a lot of land, and generally the efficiency of conversion is also quite low. And in terms of geothermal and ocean waves, these are also options, but they are practically limited, so you don't have a lot of ways to harness these. So solar is among the most prominent renewable energy technologies to actually generate power in a scalable and sustainable manner. That's simply because if we were to basically convert the amount of consumption that we project for the human energy for humans to consume, let's say even if we are to consume about 50 terawatt of power or energy, the amount of solar that can be harnessed across the entire globe is significantly larger than the overall requirement for human energy consumption, which means if harnessed appropriately, suitably, sustainably, solar happens to be the best resource for us. And my colleague Lalku here also mentioned about the different ways of converting solar to various forms, either directly to heat, and I'll talk about how we can convert that to electricity as well. So when we talk about energy sustainability for sustainable development, we have this challenge that our population is constantly growing. Of course, and that's because our needs are growing, our prosperity is growing, we are having better means and wherewithals to do whatever we want. So basically, because of that, our energy needs are also increasing. So at the same time, we want to try and ensure that the energy that we generate is through sustainable methods while also minimizing our greenhouse gas emissions. Okay, so we must, of course, at the bare minimum, what we must do is switch to renewable sources of energy. So let's think of solar as a resource for us. So this is a map of the world with the amount of solar potential. So if we look at kilowatt hour or kilowatt peak sort of ratings, whatever is red basically gives you an impression that, or it implies that there's a lot of solar that is incident on that region, and there's a great potential to harness that amount, that solar. So obviously, countries like India, North Africa, Middle East, and quite a large pocket of Australia, they are really hotbeds in this, literally and figuratively, in the sense that you can generate a lot of power through solar. Now, the other aspect is that with all of these energy the requirements and the progress that technology has made, we are no longer limited to utilizing or requiring energy during the day. When we were hunters and gatherers, decades, I won't say decades, centuries back, millennia back, we just required the day. We would sleep during the night, we don't really care about our energy needs. But now, 24/7 we need energy. So you can see that not only during the day you have to harness energy, you need to be able to utilize that energy during the night as well. So of course there's no sun at night. How do we make use of that? So that's where we have to look at other ways to either generate energy through different means or store this energy that you have generated and utilize it separately. Of course, this is kind of a solar potential, renewable energy potential for India specifically. So this is what solar can provide, and there's a lot of energy that we can get from wind as well. So this is a wind potential map, and you can see that there are places like Ladakh which are really have significant amount of wind potential, and in Gujarat and some of the southern states as well. So there's definitely a lot of potential for these renewable energy generation methods, especially in India. So what is India currently doing in all of this? So this is the overview of the Indian power sector, and this was as of 2020. Right? And as of 2020, close to 62% of all the energy generated was through thermal sources. So coal, oil, natural gas, and so on. So most of the energy seems to come from thermal energy sources. And renewables contribute only to about 25%, or hardly about 25%. And this is as of 2020. Of course, things are changing. And does anyone know what is India's target, let's say in the coming decades? Can anyone blurt out some numbers? There are targets that the Indian government has set in terms of renewable energy generation. What percentage is India planning to generate, let's say by the year 2035, 2040? So this is right now, it's 24%. Anyone has an idea what percentage the government has promised or projected? 50%, very good. Yeah, so imagine, so this has to go from 24% to 50% within, let's say, a decade or less than a decade, less than a couple of decades, right? And in terms of overall energy needs, achieving net zero carbon emission, what is the year that India is looking at? 2070, right? So it's already 2025. We are late. Okay, we need to be fast. We need to be quick. And that's a lot of energy that we need to be able to generate. But India is on a roadmap, and it's a very aggressive roadmap. So by 2022, the amount of renewable power that was generated, so it moved from about 92 gigawatt to about 175 gigawatt of installed renewable power capacity by 2022. By 2024, it increased to about 201, and it is projected to increase, again, the target is 50% by 2035, 2040. And what is the mix overall? So by 2030, the projection is within 6 years, we need to reach 450 gigawatt. So that's really aggressive and ambitious. So what is going to be the mix? The predominant mix is going to be solar, it's about 91 gigawatt, and wind, which is going to be about 48 to 50 gigawatt. So most of the energy is going to be from these two sources. So here at IIT Kanpur as well, we are looking at some of these technologies to try and keep up pace with India's ambitious and aggressive efforts towards energy generation in a sustainable manner. So what do we look at? So this is a slide that is already shown before. So what are we going to look at? At IIT Kanpur, we are looking at ways of generating energy through solar photovoltaics as well as solar thermal technologies. We also have a lot of work that's being conducted on hydrogen and other clean fuels, as again was indicated by the previous speaker. Now, this alone is not enough. Like I said, we need to be able to use or source energy 24 by 7. We want everything at our disposal 24 by 7. Right? So we don't even sleep at night these days. So we need to be able to utilize this energy all the time. So for that, we need to be able to store some of that energy to be able to use it later. And for that, we have energy storage technologies like batteries and supercapacitors. So quickly go over some of the introduction of what do we mean by energy generation through photovoltaic beams. So I'm sure many of you are familiar with how solar cells work. So this is the typical radiance or irradiation spectrum for the light that we derive from the sun. And once we see the solar spectrum, this is the region that we are trying to harness from the earth. And how do we do that? We devise a technique, or we devise a cell, which is called a solar cell, which simply has, so this is a basic structure. You have something called an absorber. You have a solar absorber that absorbs the light, generates what we know as electrons and holes. So you generate an electron-hole pair, and you have electrons going in one direction, and you have holes going in the opposite direction, and this leads to the generation of a current, electric current. And so this electric current is what we derive to power our devices and our boards. So solar cells have come in different, there's been an evolution of these cells over decades. So this has been classified into first generation, second generation, and third generation. So the first solar cells came up in the 50s and the 60s, and following that there have been a lot of developments to go to improve the efficiency overall. Okay? So we started with silicon and semiconductors like gallium arsenide. Then we moved on to thin films like cadmium telluride, CIGS, which is copper, indium, gallium, selenide, amorphous silicon, and then we wanted to put it on any other sort of substrate. So we have flexible solar cells as well. So there are dye-based systems, organic solar cells, perovskite-based systems as well. And we are constantly trying to increase the efficiency of this energy conversion. Right? So we are also trying to decrease the amount of material that we consume. So we come from about half a millimeter thick solar cell or cell to about less than a micrometer thick thin film cell, and try and achieve the same amount of efficiency that these silicon solar cells can give. The other way of energy conversion is through solar thermal beams, which the Lalto has already talked about. So you have these parabolic trough reflectors, or you have a power tower kind of a system where you have reflectors concentrating all the solar energy radiation here and helping to either directly heat or convert heat to electricity. What other methods are there for energy conversion? Of course, there are fuel cells where you utilize the generated hydrogen to actually perform an operation where hydrogen through a cell reacts with oxygen to form water, and there is energy generated through this process, and that can be utilized for a variety of applications, especially for mobility or high power applications as well. Okay. Of course, there's a lot of research going on in this. So because of this, because we have looked at energy generation, there's always a need for energy storage as well, because this is the primary challenge with renewable energy sources. Be it solar, be it wind, be it hydroelectric, they are intermittent, they are not continuous sources of power. So without being able to store the amount of the energy that we are generating, we are not able to actually utilize them as and when we need it. Okay. The other issue is, as and when we keep increasing solar and other some of these sources, we are trying to mix them with the traditional sources of generation as well, like coal and natural gas-based sources. Which means there is you have to sort of mix them, and it doesn't happen as simply as we think. So you need to ramp down production of coal and thermal-based energy and allow solar to kick in. But then when solar is down, you need to again ramp up energy generation through coal and natural gas all over again. So you have to maintain this continuous supply through this intermittent transfer as well. Right? So that is important as well. So without, I'll not spend too much time on this. There are different types of energy storage technologies, but something that I'll focus primarily on for this talk is just batteries. We have run through this really quick in the next couple of minutes or so. So energy generation is through solar photovoltaic technologies. Like I said, the first modern solar cell was produced using silicon, and this was in the late 50s. So IBM came up with this. Bell Labs introduced silicon as a cell that absorbs solar power and generates electrical energy through that. And the efficiency is defined as the output in terms of electrical power and input in terms of the light that is incident on the cell. Okay. So what are the basics? What is this basic structure? Like I said, you have a light absorber, which is typically silicon, which absorbs light, converts incident photons to an electron-hole pair. So electrons and holes are generated. These are then separated out from this junction and carried across to the opposite ends of the cell through metal contacts. And this can be connected to a load, and you can generate power from there. So what is the module typically made of? You can have cells made of crystalline silicon, multicrystalline silicon, or thin film based devices like cadmium telluride, CIGS as well. And there are so many components that go into actually making a solar module complete. Another couple of minutes real quick. Sure. Okay. So we're constantly trying to improve the efficiencies of our solar cells, and this is a very nice chart that NREL, which is National Renewable Energy Laboratory in the US, that tends to maintain, and they have started maintaining the efficiencies from 1975 all the way to 2025. You can see that many technologies have reached an efficiency up to about 20 to 30 to even 40%. So that's great technology advancement. So this is where we need a lot of research to improve some of these efficiencies as much as possible. Okay? Many of these are also kind of in mature stages of development. Market maturity is defined. So silicon is quite a mature technology, whereas some of the newer technologies like perovskites or tandem and hybrid junction cells are still in the R&D stage. But these are all in the pipeline for market commercialization. the important aspect here we need to look at is we need to choose our materials carefully. Right? So silicon being, and why was silicon chosen or why silicon makes for an obvious choice is simply because of its earth abundance and it is generally non-toxic. So silicon is among the most abundant materials on earth. So when we choose our materials, we need to make sure that we are able to cover this aspect of sustainability as well. So with that, I'll just quickly, these are just, I don't want to elaborate too much on this. I'll go straight to the last slide. I had a few slides on energy storage as well, but in the interest of time, I'll talk about what we do here at IIT Kanpur. So in the, just take just half a minute here, please. So in our material development group, where we look at a variety of technologies, our research areas primarily include topics related to solid state, lithium ion and sodium ion batteries, because we want to store the energy that we generate and utilize them quite as effectively as possible. And again, we are trying to look at sustainable methods, so sustainable materials. For example, we are trying to derive some of our components like anodes from bio-waste derived hard carbon. So we have sugarcane bagasse that's pyrolyzed, and that or even coconut husk that will be paralyzed. And in cathodes we use sulfur. Sulfur is again a high energy density as well as highly abundant resource for storing energy. Even for anodes, we are looking at silicon as a composite as well. So these are the kind of technologies that we are looking at, and again try to address this aspect of sustainability and using sustainable materials. So in terms of facilities, we have a lot of facilities to fabricate, test and build some of these devices. So all the way from lab scale coin cells to about industrial or commercial pouch cell devices as well. There's a lot of centers and support that we have from within the institute and various funding agencies as well. So with that, I again thank you all for your attention and for the time. I'm happy to answer any questions that you might have. I know I skipped a lot, but I'm always open to connect. So please look me up on LinkedIn or do my email. I'm more than happy to address any thoughts or any questions or any comments that you might have. Again, thanks for the very kind invitation to be a part of this session, and I'm truly honored, and it's a true pleasure for me to be here as well amongst you all. Thank you.
Thank you, sir, for your insightful talk. As we are running out of time, so only one or two questions.
As we are talking on the cells, so are we working on the lifespan of these cells? Because as we know that that also degrades with time.
Very good question. So the question there was, we are working on these solar cells and other these materials. Are we looking at questions of lifetime? How long are they generally useful for? So silicon-based cells are usually good for about 20 to 30 years, and they provide good stable performance over the course of time. Some of the newer generation technologies, not so much. For example, perovskites that I mentioned, they hardly last, maybe a few days. Okay, so there's a lot of research that is going on, not only to look at their lifetime, but also what after their lifetime. Okay, so silicon, as you know, there's generally a lot of issues with recycling silicon. It's great for producing energy, but then what do we do after its lifetime? So there's a lot of research that's ongoing on how can we recycle silicon and either use it in a form that it continues to provide energy or convert it into some other material or some other device. So that's a very valid question.
is a question that the solar cell, solar panel consume more area. So how can we tackle that problem?
The question on whether can we acquire that much area?
It requires more area. That if we install a solar panel, it requires more and more area. So how can we reduce the area and increase efficiency?
So your answer is in the question itself. By increasing efficiency, you will require lesser area to utilize. The other aspect is you don't need to necessarily put your solar cell on the roof, right? So sun is basically shining in a lot of places. So something that I didn't really talk about today was a topic called building integrated photovoltaics, which means there's a lot of your building that's actually available for converting even the little bit of light that comes to some sort of electrical energy. Then there is another concept called agri-photovoltaics. So you have a lot of agricultural land, which again there's a lot of sun that's shining on it. So people have put solar panels on top of agricultural fields and generate power from there. So we just have to be smart about how we use our space that is already available, and as of course we need to keep ensuring that we increase the efficiency as well, so that we minimize the amount of area that we use. There's a lot of area available.
Thank you, sir. If you also have some questions, please meet sir outside. Okay? Thank you, sir. Thank you. So now it's time to ask our next keynote speaker, who is connected to us online mode. Professor Vasudevan Subramanian. Sir, are you available? Are you connected with us, sir? So our next speaker is Professor Vasudevan Subramanian. Professor Subramanian is the Chief Scientist at CSIR Central Electrochemical Research Institute in Kanpur. He received his MSc and PhD degree in electrochemistry from Allahabad University, Chhatrapati, Tamil Nadu. His dedicated research in electrochemistry led to the conference of a BSc from Lingays University, ranked among the top 2% of the scientists worldwide by Stanford University. He has been the recipient of numerous prestigious awards, fellowships, and honors from internationally renowned organizations and associations in recognition of his significant contribution to education, research, and innovation. Dr. Subramanian has published over 120 research papers in highly reputed peer-reviewed journals and has authored 7 book chapters. He is a fellow of several esteemed academic societies and associations, including the Royal Society of Chemistry, UK, the Australian Institute of High Energy Materials, and is a chartered chemist recognized by Royal Society of Chemistry, UK. Furthermore, he served on the editorial board. And as an associate editor for several prestigious journals, including Scientific Report, Nature, Environmental Chemistry Letter, Springer Nature, and others. Now, over to you, sir. Professor Vasudevan Subramanian.
Thank you for the introduction. That is a coincidence. Is it okay now? I am able to hear. Are you able to hear my thoughts? Voice?
Sir, you are audible.
Are you able to see my slides?
Yes, sir, it is.
see my slides?
Yes, sir.
I don't know. I'm not getting any response from your side. Are you able to see my slides? Are you able to hear my voice?
Sir, you are correctly audible and slides are also visible. Sir, please proceed.
Okay, thank you. So it was delayed by 1 hour. So sorry that this delay. So I request the organizers, please see that every talk should be useful for the students and delegates. So inviting so many people is not a good thing, but the knowledge should be go to students and delegates. So I think that darshan lecture it is gone like a speed like anything. So I don't know what is the use of that type of lectures. Anyway, thank you very much for that inviting me for that this type of talk. So today I am going to talk more about on CO2 reduction and water electrolyzer. So from that you can see that 22,000 years of global temperature from the last glacial maximum of years temperature rose gradually by 3 to 4 degrees centigrade to stabilize the erosion. And now you can see, according to NASA, the global temperature have risen by 1.1 degree centigrade since late 1800. And that IPCC predicted and warns that without drastic action, we are on the track for plus 2.5 degrees centigrade, 3 degrees centigrade rise. So if it rises happen, what is going on? Climate risk. Now we are talking about climate change, climate risk like that. It is 1 point less. We are rising from 1.5 versus 2 degree. You can feel that the extreme weather and the effect of species, whatever will be, more people will be affected. So the Arctic, sea rise, so many things will happen if the temperature rises because of the seawater. We can see seawater concentration is going on increases. Now it was 3% extra. Then in the year 1000, now it is 1000. We can see in the April 2024 the concentration is 426. Now in 25 the concentration is 430. And ultimately you can see temperature is rising now a little bit less, but it is going beyond 1.30 centigrade. So these are the things we have to take more action. So if we allow, we can get the atmospheric rivers. Atmospheric rivers, we can get the very, very short period, we can get more rain. So this is because of the climate change. So we can expect more flood, then forest fire, sea level rise, and ice melting. These things will happen. So we have to understand that CO2 is a greenhouse gas having a life of 300 years of age. Even the student, the listening, their grants even will be affected because of the present CO2 generation. So still there is a controversy that so many Nobel Prize winners are. There is a controversial conversation against climate action. So because of that, they made the climate flag. You can see the what is happening in the CO2 emission. You can see the website climateclock.world. So you can find out the things. So normally this type of global, we are finding any crisis comes, the CO2 will be cut down. So you can see in the COVID, the CO2 emission will be come down to 7%. But it is not a good sign that we have to expect the crisis to reduce the CO2 emission. So we want the CO2 emission will be less in at least 2050 or 2070. So we are expecting 2050 as the net zero emission. Beyond 2050, we want net negative emission like that. So for that, India is bunch of myth, because we have to be 5 things we have to go through. So reach 500 gigawatt on energy and CO2 reduction. So many things were taken in bunch of myth. In that angle, CO2 is absorption also one of the things. So what is the indigenous benchmark for the carbon dioxide? So we can get CO2 from thermal power, blast furnace, biogas, automobile. The CO2 and other gases will be different from the different sources. For that, Sikri developed the material. So what US DO is asking, operating window is more and the CO2 absorption kinetics will be more, and it should be selective to CO2 and multi-cycle stability and the cost. So based on that, Sikri made the material. You can see, what is the millimole per gram. So we are achieving almost more than 3 millimole per gram of CO2 absorption. And you can see we are achieved almost 5 kg, 10 kg per day like that. So you can see that we have developed the material and the technology was transferred to one industry. Now we have reached 10,000 cycles like that. So this is the pilot plant production of CO2 capture material. So we are successfully making the material to absorb the CO2, and also we are developing the direct air capture CO2 material used for direct air capture. It was installed in many places in Delhi and Chennai. The progress is going on. And apart from that, we are going for the biomethanization, because you can see in the biogas plant we are getting 64.2. If you reduce the CO2 concentration, so the energy leaking for that also we are using. So after that absorption, you can make use of converting to useful fuels through the electrochemical method. So now I can come to for the hydrogen. So earlier there is a fight between batteries and fuel cells. Now there is a fight between fossil fuels, batteries and the hydrogen. So this is the graph predicted in 1956. So this is the oil age. Now we are in the hydrogen age. So now we are feeling that the prediction is correct. So this graph the liquid fuels are also decreasing and solid fuels are also decreasing. Only option is the gaseous fuel, that is the hydrogen. So in the case of renewable, in the case of PV, the current will be high in the moon time, and wind there is a fluctuation in current. So the hydrogen is the multifunctional. It connects energy, mobility, and the industry. That's why the people now talking about the hydrogen. I can say that hydrogen is the magic green fuel. Scientifically, you can see the gravimetric energy density is more than lithium-ion batteries. You can see hydrogen is 142 megajoules of kg, but in the case of lithium, it is very less. So that's why people going towards the hydrogen. And you can see the green hydrogen phosphate. You can see the hydrogen can be produced from the natural gas and many sources, feedstocks. So once you can produce the hydrogen from the water, there is no CO2 emission, there is no CCS methods used. So you can see different methods of hydrogen, grey and blue. Based on that, they make as the hydrogen. And in the case of green hydrogen, almost 0 kg of hydrogen used. The cost was now it was a little bit higher, but it is going on decreasing. These are all the different methods you can produce the hydrogen. So now we want the hydrogen from the renewable. This is the production of hydrogen with electricity from renewables. You can make the electricity from renewable sources like hydro, wind, bio. Then all the energy should be passed to the electrolysis. You can get the hydrogen. So this is called the production of hydrogen with electricity from renewables. So this is the production of hydrogen without electricity, but it is renewable. You can use the biological sources of energy like bioelectrochemical speaking, fermentation. There are many methods of renewable sources are available, but there is no time. So this is the head history of electrolysis. You can get the literature because of the time constraint. I am not going to make these slides. So in secret we are concentrating on protonic chain membrane and alkaline water electrolysis and also the ionic exchange. So secret is more concentration on the low temperature electrolysis. These are all the pros and cons because of the time because I work for 1 hour. So the time is very less, so there is no use of studying these things. So this alkaline electrolysis is the king of the electrolysis percent. And I can say that PM and AM are the teenage challenges. So before going to the electronics research, you have to see this graph. We want the energy consumption will be very less equivalent to the petrol and other things. So for that many approaches are there. Suppose you can see now, we want electrolysis, there is a cathodic and anodic reaction. For that, if you want to go here, the voltage should be 1.2 V. The cathode, I can say the platinum is the overproduction is less. So another option is if instead of OER, you can make this type of chemicals in the anode so that you can reduce the energy consumption. Mostly nickel is used in alkaline medium and platinum and palladium is used in the acid medium. So this is the general concept. And you can also see this is the literature in the case of hydrogen emission. This is a 3-step reaction, 3 polymer and hydrogen tapered step. Our goal is to reduce the platinum content. There are many methods. This is one of the methods. You can reduce the content of platinum deposition or usage in the electrolyzer by the chemical deposition that you can cause platinum and reducing agent. Thereby you can reduce the platinum. And also you can make the supporting material like carbon so that you can make 60% of platinum or 10 or 20%. So these volcano plants will give the which material will be good for the ICSEAM and the other things like anode catalyst also you have to prefer. This is a 3-step reaction. The more concentration will be go for the oxide emission materials like butyl, perovskite, spiral type. Which medium you are, if it is the acid medium or PEM electrolyzer, you can go for butyl, alkaline, perovskite, spiral. Mostly iridium will be used in the PM electrolyzer because the iridium, you can see the platinum and iridium cost will be going on rises and the availability of iridium also less. Then you have to go for the alternate material. Apart from the catalyst, the electrolyzer is using the current collector also very important. Now people are using metal current collectors. Once the research is going on the composite material, it is good for the research. So this is the PM electrolyzer concept. This is the protonic chain membrane. You can pass water. You can get hydrogen and oxygen from the anode and cathode. Respectively, many catalysts are trying in all over the world. For example, iridium. There is the iridium T8 by many cathode. We optimize the catalyst. This is the first prototype developed in Sikri in almost 2025 years back. And still now we are going on in increasing the capacity. This is the full-fledged 1000 liters of electrolyzer, and now at present we are making the 6000 liters of electrolyzer. This is Sikri's concept, and we are going on doing the how to reduce the platinum and iridium. These are all the higher scale cells. Technical specification, you can see that we are on board with the international standards, and this technology was transferred to the Eastern electrolyzer. They are going on implementing in many places. Now we are trying with the solar panels. So the DOE is given the target for 2050. What is the current density, energy consumption, so many things. So we are going towards the DOE concept, and you can see our Sikri's electrolyzer is very highly competent in the international market. Like that alkaline electrolyzer, here there is only diagram, there is no ion exchange membrane. So here we are using the many catalysts, pure nickel, granny nickel, so many things. If you see the nickel demand will be rises big, but the nickel availability is more. But the people are talking water availability, but for electrolysis, water availability is very, very less compared to other systems with the hydrogen. There is no problem with the hydrogen. For that alkaline electrolyzer, we made the electrode technology like 20 years back, that is also transferred. Now we are making the alkaline electrolyzer for the Indian purposes. We are also making many catalyst development, and we are not doing any high temperature electrolysis. This is timeline we started the research in 1996. It is we are not stopped anywhere else. It is going on, and 2030 target is megawatt electrolyzer. These are all the upcoming electrolyzers called ICSEAM electrolyzer and direct electrolysis. There is still advanced electrolysis called capital. This field also we are doing, and we are also going for the non-noble metal catalyst and photoelectric methods. This is the typical method we have for the TiO2. We are sandblasting the titanium sheet using this sand. So when we are seeing that surface of the titanium sandblasted titanium, we found that that is what the SiO2. Because of the temperature in the titanium, we got like TiO2 SiO2 catalyst. So like that TiO2 Al2O3, and we preferred in a non-metal based CN4 So like that we are doing many photoelectrochemical methods, and also because of the iron availability in India is more, for that we are now preferring the electrode used in the ferrite. That is iron based catalyst. We are also doing SO2 electrolysis to get sulfuric acid. We are making that hydrogen to convert the CO2 to methanol and also the green hydrogen. Now we are getting the people are now talking the golden hydrogen. That is, we are getting the hydrogen from the underground. This type of research is also going the CSEAM components. This is the first trend developed in China. The zero area is going to plan for 2040, that is 200 C. Berlin started the complete hydrogen airport. So the cost wise now it was a little bit more, and 2050 you can get the very cheap hydrogen. And you can see the readiness and confidence level. People are going on making the graph readiness and also the confidence level. Because of the time I am not able to explain these things. The challenges, hydrogen will be used in cement industry and ammonia industry and also the steel industry. And these are all the various challenges by the various departments, materials science people, electrical people, mechanics, electronics. So we have to, everyone has to concentrate for the hydrogen things. And India is going for the very big plan for the hydrogen valley, that is production, storage, utilization, and SIGRI is going to be part of hydrogen valley. This is the hydrogen station in open in Silicon Valley. So now the vision for this 2047. For that India is making a hydrogen mission. So already many players have started the green hydrogen. So all these things you can see the hydrogen demand in India is very, very high, and you can see CAGR, that is compound annual growth rate, is very, very high in 2040. That's why industries are going for the hydrogen. And UP and Gujarat are expected to be the hydrogen consuming states now. And you can see the hydrogen demand increases, we have to increase the global renewable capacity also. India is the renewable sources also little bit high. Going on, the cost wise, India Ayok want very less cost, but green energy cost is little bit higher. All institutes are going towards the cost reduction in the things. And also you can see that next month we are going to start the green hydrogen train. We compared the anything using a train with diesel, electrification. that where hydrogen can be less CO2 emission and highly cost. Already many places hydrogen bunks are started, and NTPC launched green hydrogen buses. In India, the Prime Minister of India started this one. So what will be the fuel of the future? That is, it was given in 1874. What will one day be employed as a fuel, that hydrogen oxygen, which constitute, they use this singly or together, will furnish an inexhaustible source of heat and light of an intensity of which code is not capable. So this statement was given in 1974. Now we are realizing that is a environmental point of view. Hydrogen is also warming effect because the formation of methane to the water content. So these things because of the water also very good for the electrochemical water treatment. But for the academic research to industrial research, you have to pass the value of time. So this is very, very important for the content. So always electrochemistry is people and planted something, carry the torch for a sustainable future. Thank you very much.
Thank you, sir, for your insightful and awakening talk. I would like to ask audience to have questions. Please ask if you have any questions. If no questions, thank you, sir. Thank you, sir, for your insightful talk. Thank you, sir.